So the roller coaster starts right here with zero velocity. This is explained in here. I'm just paraphrasing. And there's this force, a 1,120 Newton force, that pulls or pushes the roller coaster up to here, where it comes to a stop. So it's not moving here, it goes up to there, and it's not moving. It has to move along the way, but once it gets to here, there's some infinitesimally small nudge, and then it starts to do what roller coasters do, totally frictionlessly from B until D. So there's no extra push, there's no force of friction, only gravity affecting it here, no air resistance. Once it gets to D, the thing hits the brakes, and there's this 500 Newton braking force to the left, which is going to slow it down, but not enough so it'll stop before it gets to the cliff, and then it goes off the cliff down to F. So this part, this fall through the air, we're assuming that is frictionless too. So these two places, from A to B and from D to E, these are the only intervals where energy is not, or mechanical energy is not totally conserved. In this first part, mechanical energy is being energy is being added to the cart by something outside the system, and here energy is being removed from the cart by a force from outside. But in these segments, energy is conserved. Total energy does not change. So to figure this out, the first step is, you could do this different ways, but I think the first step is to get the heights. So if this height is 90 and this is 30, then C and D and E are at 60. And if E and D and C are at 60 and this is 30 lower, then F is at 30. Potential energy, we can calculate all these potential energies for these for B, C, D, E, and F, because that's just mass times G times height. We know the heights, we know the mass is 200 kilograms, so this is going to be 200 times 9.8 times 90, and that, looking at my cheat sheet over here, comes out to 176,400 joules. And if I do the same thing, except I'm doing 200 times 9.8 times 60, then we get 117,600 joules. And that's going to stay the same here and stay the same there because all these heights are the same. Same potential energy. Now we're 30 meters lower, so MGH is going to be 200 times 9.8 times 30, and that's 58,800. I can do some kinetic energies where velocity is 0. Kinetic energy is 1/2 mv squared, so if velocity is 0, kinetic energy is 0. And the next thing I can do, actually there's something else I can, well, I don't know if I can, anyway, I was going to say, I'm not sure if I can really start on, I guess I can start on A if I want to. I'm not going to. I'm going to save that for last. So I can add this potential energy and this kinetic energy to get the total. Total is just going to be the same as the potential energy, 176,400. So up here at the top, that's at letter B. It has a lot of potential energy because it's up really high, but it doesn't have any kinetic energy because it's not moving. Total energy is that. Now, as I said earlier, since there's no friction between B and C and D, the total energy is going to be the same here. There's no energy loss. And I could go through the steps of writing this out. I could say the kinetic energy at B plus the potential energy at B equals the kinetic energy at C plus potential energy at C. And I could plug in all these values and I could solve, but it's since I know this total already, I can just jump right to that total. What I mean by that is the total energy here is 176,400, so the total at C is going to be 176,400. And if I wrote everything I knew out here, the only variable that I would not have an answer for is this one. I'd know this, I'd know this, I'd know that, and I could solve for that. But I've really got that same thing set up here. I know the starting potential energy, starting kinetic energy. Here is the final potential energy, so I can get the final kinetic energy because this plus this has to equal this plus this. Another way of saying that is these two have to add up to the total. So if the total remains the same at B and C, I can just subtract the potential energy to get the kinetic energy. 176,400 minus 600 is 58,800. Kind of a coincidental number there. And I can keep doing this. At letter D, we've got the same potential energy. We also have the same total energy because there's no friction here. There's no work done on this from outside the system. So the total energy is conserved. And since the potential energy stays the same all through here, the kinetic energy also does. But that's not true in this segment because there's this extra outside force. So to finish up here, to do this part, I am going to use a different formula. And the formula is this one. Whenever you have work by some outside force, either work that is like in friction, or maybe these brakes taking away energy, or it could be something adding energy, you use this formula. So this is what I'm going to do. Let me write it out a different way. So I'll write, since I'm talking about this is the initial position, this is the final position, I will say that the kinetic energy at D plus the potential energy at D, that's all the energy it has at D, plus some work that's being done on it between D and E, equals the total energy at E, which is the kinetic energy at E plus the potential energy at E. And now I can plug some stuff in. The kinetic energy at D was 58,800. And the potential energy at D was 117,600. The work that's being done, since the car is going to the right, and the force, this is a braking force, it's a leftward force, it's going to be a negative 500 Newton force. The work that's being done here is negative 500 newtons times the distance, 40 meters. So it's going to be negative 20,000 joules. Now, if you didn't put that sign in right and you figured out it was 20,000 joules, you could just do some thinking and say, well, the braking is actually going to slow this down. It's going to take away energy. So I need to subtract that. So this work's going to be negative work because it's taking away energy. Let me get rid of the positive sign, or the plus sign. Minus 20,000 joules. And that equals these two, the kinetic energy that it's going to have after, plus the potential energy. And I know the potential energy at E. Potential energy is the same for all three of these. It's 117,600. This is a very simple thing to solve. And trust me if I just give you the answer. This plus this minus that gives me 38,800. So this is 38,800. So the kinetic energy had been 58,800. Now it's 38,800. So it's the kinetic energy that gets lost here. The potential energy doesn't change. That energy comes away from kinetic. And the total is going to be 117,600 plus 38,800, which ends up being 20,000 less than what the total was before. So there, we've figured everything out at E, except for these velocities. These velocities are easy. I'll come back to those in a second. Now for F, F's an easy one because there's no friction here. There's no extra work done. So the total energy has to be the same. And if the total energy is the same, and now this is the new potential energy, then the kinetic energy has to be the total minus the potential, and that turns out to be 97,600. I mentioned these are easy. So if kinetic energy equals 1/2 mv squared, if I want to solve this for velocity, I can just multiply both sides by 2 times 2 and divide both sides by m. So, and then take the square root of both sides, and I've got it. So the velocity ends up being the square root of 2 times the kinetic energy over the mass. And the mass is 200 kilograms. So to find this velocity, it's going to be 2 times 58,800 divided by 200, then take the square root of that, and it comes out to 24.2. And that's going to be the same for D. So this should make sense. This is going to speed up coming down the hill, but once it gets to C, it's going to stay the same speed. The only thing that would slow it down is if there's air resistance or friction, but we're assuming that there isn't. When you multiply this kinetic energy by 2, divide by 200, take the square root, you get 19.7, and then this last kinetic energy is 31.2. All that remains is to figure out what's going on at A. So A is the reverse of what happened here. When I say here, I'm talking about between D and E. Between D and E, negative work was done by this brake that was pushing backward. So you can see the kinetic energy that it had plus the potential energy that it had, we're subtracting from that negative work to give us the new total energy. At the beginning, there's a push in the direction that it's moving. It's actually having energy added to it. So I'm going to use the same formula. I'm going to write this same thing, except I'm going to use different letters and substitute some different stuff. You can always use this formula if you want. You could use this in a lot of places, but if there's no non-conservative work, then that just becomes 0. So the kinetic energy at A plus the potential energy at A plus any work by an outside force, which is going to be this force that's acting on this cart, equals the total energy at B, which is the kinetic energy at B plus the potential energy at B. And kinetic energy at A, I know is 0. I've already done that because the velocity is 0. So 0 plus, I don't know the potential energy at A, but I'd like to find out, and I will, right here. Plus the work. Now the work is this force over that distance. So 70 newtons times, 70 meters times 1,120 newtons. And that's positive. That's a force in the direction that it's moving that's adding to its energy. And that's going to equal the kinetic energy at B, which is 0, plus the potential energy at B, which I've already found, 176,400. All right, so this is a very doable thing. I don't think I've written down this number. It's like 78,000 or something. But so if you multiply this together, subtract it from this, then you get the potential energy at A. The potential energy at A ends up being 98,000 joules. And since mgh equals the potential energy, I can say that 98,000 equals 200 kilograms, that's the mass, times 9.8 meters per second squared, times the height, and I can solve for the height. So it's 98,000 divided by 200 divided by 9.8, and it comes out to 50 meters. The last thing to fill in is the total energy here, which is just the kinetic energy plus the potential. And I'm done.